All right, so for this example, we're going to be graphing a function, but we're not going to be doing it the way you may be used to. We're going to be doing it using exclusively the first and second derivative tests and just a little bit of, thinking. So here's our function that we're going to be graphing. F of x is equal to x minus x cubed over 6. So first things first, let's take the first derivative of this. Well, that's going to be 1 minus 3x squared over 6. Of course, that 3 reduces, so I get 1 minus x squared over 2. Let's go ahead and analyze f prime here. Where is f prime equal to 0? It's going to be equal to 1 minus x squared over 2. Let's go ahead and solve this. I'll add the x squared over 2 to both sides. Equals 1. Multiplied by 2, I get x squared equals 2. And so I get x is equal to plus or minus the square root of 2. So if I construct an interval right quick, negative root 2 to positive root 2, and keep in mind that as far as points go, these are the points, negative root 2, well, for f prime, these are the points. But remember, if we actually want to point on the graph, I'd have to plug this back in here, and I don't particularly want to do root 2 and root 2 cubed, so we don't need to do that. I'm just going to look at where f prime is positive or negative. So in between these two values, if I look at f prime, if I plug in 0, I would have 1 minus 0 squared over 2, which is just 1, and that is positive. Now I go on both of these sides. If I do anything less than negative root 2, I'm going to have 1 minus, since I'm squaring it, it becomes positive, 1 minus something bigger than 1. And so this is going to be negative. And likewise over here, 1 minus something bigger than 1, because if I square anything bigger than square root of 2, I'm going to have something bigger than 2 over 2. And so this is going to be negative over here as well. So I have that information, that f prime is equal to 0 at these two locations, and it's negative outside of that interval right there. Now, let's go ahead and look at f double prime. F double prime, I just take the derivative of this again. Until the 1 goes away, I bring down the 2. So I get negative 2x over 2, which is just negative x. All right, f double prime, where does that equal 0? Well, since I just have an x, that's just going to be equal to 0 at 0. So let's investigate that interval as well. All right, if I pick something less than 0, well, negative anything less than 0 is actually positive, right? Two negatives make a positive. And then over here, if I do negative of a positive number, I get negative. Okay, so what does all this information flying around tell us? Well, it tells us that at negative and positive root 2, the slope of our graph is going to be 0. And it tells us that the slope is positive in between those values and negative outside of it. F double prime tells us that our inflection point is going to be at 0, so the place where the concavity switches, or could switch, and that to the left of that, we have positive or upwards concavity, and to the right of 0, we've got negative or downwards concavity. So let's use this information to construct our graph. And let's say negative root 2 is like right here, and positive root 2 is like right here. And there's 0 right there. Okay, so again, just using the information we have, we know that there should be a positive concavity over here. And we know that the slope should be 0 at negative root 2. So wherever I put my upwards cup, I know that it's going to be flat right here at negative root 2 because the slope is 0, and it's going to be an upwards cup. I also know that we have to go through the origin, right? We know that at 0, if I plug that in, 0 minus 0 cubed over 6 is 0. So we know we have to go through this point. So you can think about this. If I put the cup up here, in order to go through the origin, I'd have to curve back down to get there. But when we do our derivative tests, it doesn't tell us that at any point the slope becomes negative. In fact, it tells us very explicitly that anything after negative root 2 should be a positive slope. So I can't be curving back down like that. So I know this has to be a positive slope. I also know that I should have a 0 slope here. And what else do I know? I know that to the left of negative root 2, I should have a negative slope. And so it should be going down like this. If I put all that information together, I'm getting something that curves like this. Again, because it's concave upward, I know that over here I need a negative slope until I've got a 0 slope here and a positive slope here. And I know the cup has to be down here because otherwise I'd have to curve down to hit the origin. That's how I'm able to construct that just from here. And I don't really know for sure what the graph does at this point, so I'll just sort of extend it like that. Okay, now let's do the same analysis over here. Over here, I'm supposed to have a negative concavity or a downward cup. Well, for the sake of argument, let's say I put it down here. What does this tell us? It tells us right here, I'm supposed to have a positive slope. So again, there's no way I can have the cup down here because I would have to curve down to meet it, right? But it's a downward cup. I'm not allowed to do that. I'm supposed to have a positive slope. All the way up until root 2, at which point my slope will be negative. And I've got a downward cup. So the same reasoning is happening here. I can't curve down like this because it explicitly tells me that I've got a positive slope all the way up until this value right here. Then it tells me I have a 0 slope at that point. And then everything past this point should be negative slope. And I've got downward concavity, so it goes like this. So there we go. Just using my derivative tests and looking at the function, recognizing that I do need to go through the point 0, 0, I can just look at this and just using where the slope should be negative, where they should be 0, and where they should be positive, and where I should have an up cup or a down cup, positive concavity or negative concavity, I can construct the graph just using that with very minimal reference to actually plugging points into the function. Now, let's go ahead and check this with the graphing calculator. So I'm going to go ahead and put this function in. So I hit y equals, and I'm doing x minus x cubed. Now remember when you use the little caret up arrow, make sure to press to the right to bring your cursor down, boop, and then divide by 6. Now I'll just look at the graph right away. It's probably going to need some adjustments to the window, but let's see what we got. Okay, so you can kind of see what I'm talking about, but we're also being very narrow here, right? We're only looking in this very small range. So if I look at that, I think what I'll change the window to is, so it looks like between -3 and 3, and then I'll just make the y values go between -2 and 2. So I'll make x be -3, x max be 3, I'll let y be -2, and y max be 2. Let's regraph it. Cool. Nice. So you can see looking at this that this matches what we would expect with the graph. One more thing I'm just going to double check. Let's check these 0 points here. If I plug in the value of negative root 2, well, that's not going to give me 0 in the function, right? But I'm expecting the cursor to go at that lower point and the upper cursor to go to the higher point. So I'm just going to do that. Second, calc, and I'll plug in a value of the square root of 2 and hit enter. Yep, so it's highlighting that upper area right there, just like we'd expect. Let me do the same thing for negative root 2. So negative square root of 2. Whoops. There we go. Yep, exactly as we'd expect. It's highlighting that area right there. So there we go. Just using first and second derivative tests and being very careful about putting all that information together, we were able to fairly accurately recreate this graph. And the only point we ever actually plugged into the original function was just 0, 0. So that is this example.